So today we're going to be talking about fluid flow of immersed objects, specifically packed beds. Um, so to start, there are two types of forces that a fluid exerts over an immersed object. The first is skin drag, and skin drag is a frictional force that is exerted in the same direction as the flowing fluid. Um, so the formula for skin drag is equal to the integral of over the entire surface of tau at the fluid-liquid interface, which tau is the shear stress, which is equal to our viscosity mu times the velocity gradient dv dy at our interface I. So we'd multiply our shear stress by our by cosine theta, and this is just because we're trying to isolate the force in the direction of the overall flowing fluid. So if we look here, we have our flowing fluid over the sphere. The force is in the direction of the fluid at that time. However, the rest of the fluid that isn't deformed is still moving in this straight line, and we want the force in reference to that straight line. So we would take this angle theta and find the cosine of that angle, and that would be our resulting force. And then, of course, it's with respect to area. So this is our skin drag equation. The other type of force is known as form drag, and this actually takes into account the geometry of the object that is being flowed over. So look at the sphere in this image right here. So a bulky object like a sphere, as fluid flows over it, eventually the boundary layer will separate from the sphere itself, and it'll form this separation area right here. This area is very turbulent, categorized by like vortices and a very low pressure. The low pressure being the important part for this. So what that low pressure will do is it'll create a pressure gradient where we have this high pressure up at the front and a low pressure at the back. And that will push the object towards that low pressure region. So how do we express this mathematically? Well, we have the form drag force is equal to the integral over the surface, same as skin drag, of the pressure times sine theta, and this is just because the force is orthogonal to the skin drag force or the flowing fluid at the time. So we use sine theta instead of cos theta to isolate the force, the component of the force in the direction of the overall fluid. And then it's with respect to A again, area again. So our overall drag force is equal to the integral over the surface of tau at the interface times cosine theta plus p sine theta, all with respect to area. So with these concepts in mind, let's compare this bulky object to this more streamlined object. So first, looking at the bulky object, we see this high separation area, and that would mean we have a higher pressure gradient and the form drag would be higher. Here on the streamlined object, however, we have a very low separation area, and therefore the form drag would be lower. And then with skin drag, there's far less contact surface area on this bulky sphere than this streamlined object, so we would expect the skin drag to be a lot higher in this streamlined object. Now, this equation right here is actually not very useful in the real world. It's nice to look at to understand the concepts. However, it's very hard to isolate those individual components in the real world. So what we do is we generalize and compact everything into a coefficient that we find experimentally. So our drag coefficient up here, it is equal to the drag force times the reference area. The reference area is it depends on the object, but in the case of a sphere, which we'll be looking at for the rest of my section, it is equal to the projected area of that sphere in the direction of the bulk fluid flow, but it would be the same projection in any, because it's a sphere, it would be the same regardless of what direction you're projecting it. And that would be equal to pi dp, which is the same as the normal diameter, squared over 4. Yeah, so it's the force times the projected area over the density rho and the free stream or bulk velocity v naught squared, and then all that over 2. So yeah, we can also isolate the force from this, and we get this equation here. And then another important number for fluids is the Reynolds number, which in the case of an immersed body is the diameter, the projected diameter times the free stream velocity times rho over mu, the viscosity. So yeah, those are our 3 big constants for, or our 3 big variables for a fluid flow over an immersed object. And typically the relation between the Reynolds number and the other 2 is not very clean. However, in very specific instances, we can find an exact solution. And this is one of those instances. So when we're looking at the laminar region of a sphere with a Reynolds number less than 1, we get an exact solution. So this solution for force comes from Stokes' law. And we can use it to find an exact relationship between the drag coefficient and Reynolds number. So by substituting the drag force in, we get CD is equal to 3 pi mu dp v naught over AP all over rho v naught squared over 2. And we know from earlier, because we're looking at a sphere, that the projected area is equal to pi dp squared over 4. And then all the algebra will net us 24 mu over rho v naught dp. And you can do this yourself. It's pretty simple. But if we look at this part right here, this actually turns out to be 1 over Reynolds number. So our final solution would be CD is equal to 24 over Reynolds number. Now, this is, again, a very particular instance where the numbers play nice, but usually we will not get an exact solution like this. So what we have down below is a chart that relates Reynolds number. In this case, it's drawn as NRE. That's just how the book Giancopoulos described this. But yeah, it relates the drag coefficient to Reynolds number. So if we look at our region before for a sphere, which is about here to up here, we see that it pretty much obeys our law, as in it starts at a reasonable number and then it shoots off towards infinity, which is what we'd expect as the number gets smaller and smaller. However, going forward, it's a little more complex. It has this little bump here, and then it plateaus for a while, and then it drops off. And this drop off is just because the boundary layer becomes turbulent. But yeah, so typically the way we use this in a problem is we get our fluid characteristics, and from that we get Reynolds number. And then we'd look at this chart here to relate Reynolds number to the drag coefficient using the shape. And then from that, we use other information to get the force, drag force. So yeah, that's how that all works. Now that we have the basics out of the way, we're good to move on to packed beds. So a packed bed is basically just a bunch of particles packed very densely, and then you have fluid flowing through those particles. So one assumption that we will be making for this is that the particles are evenly distributed and that there is no channeling. Basically means that the particles are just like I said, evenly distributed. There's no clumps or voids that are disparate from the rest. And no channeling means there's no large gap that the fluid will prefer to flow in rather than the denser packed molecules. Now, in this picture, they're shown as circles or spheres. They can be any shape. They can be cylinders. They can be oblong. They can be abstract, irregular, whatever. But yeah, those are packed beds.
To describe laminar flow in packed beds, the first variable we need to define is the void fraction of the bed. The void fraction is the ratio of the volume of voids in the bed to the total volume of the bed. And it's used to tell how much of the total volume in the bed is available for fluid to flow through. We can also define the specific surface of a particle of the bed as the ratio of the particle's surface area to its volume. This is also equivalent to 6 over the effective diameter of the particle, where the effective diameter, dp, is equal to 6 over the specific surface. From the specific surface and void fraction, we can define the total surface area ratio A as the specific surface times the concentration of solids in the bed, which is 1 minus the void fraction. Lastly, we can define the superficial velocity V prime equal to the void fraction times the average interstitial velocity V. This represents the flow rate across the entire bed as a product of the void fraction times the flow rate across gaps in the bed. To define the Reynolds number of a packed bed, we must first define the hydraulic radius, RH, as the ratio of the flow area of the bed to the wetted perimeter of the particles in the bed. This is also equivalent to the void fraction over the total surface area ratio. We can substitute 4 times the hydraulic radius as the characteristic length in the Reynolds equation, as shown here, and obtain a coefficient of 4/6. However, for convenience, the Ergun equation replaces the 4/6 and also adds G prime as the superficial velocity times the density of the fluid, where G prime represents the mass flow rate in a cross-section of the bed. For low Reynolds numbers, we can describe the laminar flow pressure drop using the Hagen-Poiseuille equation for laminar flow. We have the pressure drop with a coefficient of 32 over the characteristic length squared, and when we substitute in the hydraulic radius times 4 for the characteristic length, as well as terms for superficial velocity, we find a new coefficient of 72. However, the true path length for packed beds is often significantly larger than predicted, which is why a coefficient of 150 is used in the Blake-Kozini equation. Alternatively, for high Reynolds numbers, we can describe the pressure loss for turbulent flows using the friction factor as a coefficient. With this equation, we have 3 times the friction factor as the leading coefficient. However, experimental results have shown that this leading coefficient can be approximated as 1.75, which we see in the Burke-Plummer equation. We can combine the pressure drop equations for both laminar and turbulent flow to get the combined general equation for any Reynolds number. The pressure drop is equal to the laminar flow term plus the turbulent flow term. For high Reynolds numbers, the turbulent flow term is going to be more significant, and for low Reynolds numbers, the laminar flow term is going to be more significant. We can also rearrange this algebraically to get a dimensionless form, shown here. To accurately model the pressure drop in packed beds with non-spherical particles, we need to define the sphericity of the particle of a packed bed. This is equivalent to pi times the effective diameter squared over the surface area of the particle. A sphericity of 1 is equivalent to the sphericity of a sphere, and the shape factor decreases as you get further away from the sphere. We also have the specific surface of a non-spherical particle, AB, again in terms of the sphericity, which is 6 over the sphericity shape factor times the effective diameter. And we also have the updated total surface area ratio for non-spherical particles. To model the pressure drop for packed beds with multiple different sized particles, we also need to calculate the mean surface area of the packed bed. This is equivalent to the sum of the concentration of each type of particle in the bed times its specific surface area. Additionally, we can calculate the mean diameter dpm as 6 over the specific surface area, which can also be written in terms of the sphericity shape factor. As you can see in the packed bed below, there's two different sized particles, one larger particle and one smaller particle, as well as mixtures between the two. Lastly, we can look at Darcy's law for flow in porous material. For the purely viscous flow, we have the superficial velocity equivalent to the negative porosity times the pressure drop over the viscosity times the length. And this equation is extremely useful for looking at oil reservoirs, where the porosity greatly impacts the flow of oil through reservoir rock. That's all we have for stationary packed beds.
We're going to discuss flow in fluidized beds. So fluidization occurs when there is a fluid flowing upward through a particle bed. And so as you can imagine, there is a force, gravitational force acting down on the particles because of their mass, but as the velocity increases, the pressure drop increases, and there is a force caused by this pressure drop acting upward on the particles. And so eventually at a certain point, as the force acting upwards increases, it will equal the force of gravity, and at this point particle movement will begin to occur, and that is known as the minimum fluidization point. And so the velocity at which fluidization occurs is the minimum fluidization velocity, and the porosity at which fluidization occurs is known as the minimum fluidization porosity. And so here are some typical values for the minimum fluidization porosity based on particle size and shape factor. And so you can experimentally determine the minimum fluidization porosity by measuring the height of the bed, the minimum fluidization height. And so and that's because of this expression here. So you can relate the volume that particles take up to the height and porosity. And so assuming that the volume that they take up is held constant, that allows us to derive these following two relationships. And this allows us to relate the fluidization height and fluidization porosity for a fluid bed, two different minimum fluidization heights and fluidization porosities. So also the force caused by a pressure drop is equal to the gravitational force that is acting on a particle minus the buoyant force that is acting on a particle. And so this results in these two equations here. But often the particles are of a regular shape, so you want an equation that accounts for shape factor and particle size. So substituting in the shape factor and particle size into equation 1, we get equation 8 here. And if you combine equation 7 and 8, you can get this equation in terms of the minimum fluidization velocity. And if you replace the if you substitute Reynolds number in for the minimum fluidization porosity, you actually get equation 10 here, which allows us to do further simplifications based on the particle size. So for small particles, you can cancel out this first term here and get equation 11, and then for larger particles, you can cancel out this term in the middle here to get equation 12. Now, in some cases, you won't know the minimum fluidization porosity or the shape factor, but for a variety of systems, these two equations here will allow you to still calculate the Reynolds number. And so by substituting these two values into equation 10 and solving for Reynolds number, we can develop equation 13. So solving equation 11 right here for the velocity, we get the following expression, and this is only valid for small particles. And so it is found that this term right here, all of that is constant, and so it can be expressed as a single lumped together constant K1. So the flow rate of fluidized bed is actually also limited by the entrainment of solids from the bed. So the actual maximum allowable velocity is approximated as the terminal settling velocity of the particles, and there are some expressions for that. So for fine solids, you can use this expression, and then for larger solids, you can use this expression to determine that. So let's go through a couple of examples here. So there's solid particles that are fluidized using air, and the following properties are given. So let's calculate the minimum fluidization height. So we know that the volume is equal to the minimum fluidization height times the area times 1 minus the minimum fluidization porosity. And so we have that is given right here, and then we also have the minimum fluidization porosity. So we just need the volume. So they also give us the particle mass. So we know that the volume is equal to the particle density over the particle mass, which in this case is 0.3 meters cubed. And so we can plug that all in to get LMF is equal to volume over area times 1 minus the minimum porosity, and that will get you 1.724 meters. Alright, so now to part B, calculate the pressure drop. So this is pretty simple. We're just going to use this equation. So the pressure drop is equal to 1 minus the, so it's the minimum fluidization height times 1 minus the minimum fluidization porosity times the density of the particle minus the density of the fluid times gravity. So once you calculate that, you'll get that is equal to 9.78 times 10 to the third pascals. Okay, so part C is a little bit more complicated, so it wants you to calculate the minimum fluid velocity. So we're going to start by using equation 10. So you have 1.75 over shape factor times math is times the Reynolds number squared plus 150 times 1 minus minimum fluidization porosity over shape factor squared fluidization porosity cubed. What's Reynolds number minus? And so you're just going to tabulate these constants and use them to solve the quadratic equation. So you're going to get A is equal to 26.84, B is equal to 1516.4, and C is equal to negative 117.8. And so by using the quadratic equation, you'll get that the Reynolds number is equal to 0.076776, and also that it's equal to negative 56.6. But you know that this cannot be true because the Reynolds number must be greater than 0. So then, just to calculate the minimum fluidization porosity velocity from that, you know that is equal to the Reynolds number times the viscosity divided by the particle size times the density, which in this case is equal to 5.03 times 10 to the negative third meters per second. Okay, so D wants us to do the same calculation, but this time assuming that the particle size and the minimum fluid porosity are not given. So in this case, we're instead going to use equation 13, and so in this case, we'll get that the Reynolds number minimum fluidization is equal to 0.0712, which is still very close to the one we calculated in part C. And then using the same method, we're going to calculate the minimum fluid velocity, and we'll get, in this case, it's 4.16 times 10 to the negative third meters per second. Alright, so example 2 wants us to use the data from example 1 to estimate the terminal settling velocity. Alright, so recall that the Reynolds number is 0.0776, and so that is less than 0.4, so this equation is valid for approximating that. So we know that Vt is approximately 90 times the minimum fluidization velocity. So in that case, that is going to be equal to 0.453 meters per second. Okay, so B wants us to estimate the porosity of an operating velocity of 3 times the minimum fluidization velocity. So the operating velocity is going to be equal to 3 times the minimum fluidization velocity, which is in this case going to be equal to 1.51 to the negative 2. So to do this, we're going to use this expression equal to K1 times the porosity cubed over 1 minus porosity. And so we have the minimum fluidization porosity and the minimum fluidization velocity, so we can calculate K1 using that, and so we'll find that K1 is equal to 3.94 times 10 to the negative 2, and so plugging all of that in, we'll find that times 10 to the negative 2 is equal to 3.94 times 10 to the negative 2 times porosity cubed over 1 minus porosity. And so solving this, we can find that porosity is equal to 0.555